Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 24. We're talking about the ANOVA table in applied regression. So last time we talked about correlation and the relationship with the straight line regression. We defined a new quantity called the coefficient of determination, and it tells us what percentage of the total variation in y, our response, is accounted for by the regression line. We talked about how big it should be in practice. If we're going to use it for prediction, then if we're going to use our equation for prediction, we should have an r squared of at least 0.5 or very close to that, and we'd love for it to be higher. We talked about the test for hypotheses. We talked about a test for rho equals 0 versus it's not. So is it significant or is it not significant? And then we also talked about testing rho against other numbers besides 0, and for that we needed a Fisher transformation. We also discussed how to do a confidence interval for R. The ANOVA table, this chapter we're going to talk about the ANOVA table, and with it the fundamental equation of regression analysis, and then how we can use this for some hypothesis tests. So let's take a look at an ANOVA table. So first we have the model, which is the regression line, then error, and then total. So everything here is based on the line that explains the data. So SSR is the sum of squares of regression, and this is added to the sum of squares error to give us the total sums of squares, or the sum of squares of y. So sometimes this is called SST. And the relationship is the SSR plus SSE equals SSY or SST. It also turns out that for the degrees of freedom that we have degree of freedom regression plus degrees of freedom error equals the degrees of freedom for the total. Okay? And so that's nice. So if you look at this, 1 plus n minus 2, well, that turns out to be n minus 1, which is exactly what we end up with for the total. Now, we have these new quantities here called the mean square. Can't hardly read that. Mean square. All right, so what we do is we take the sum of squares and divide it by the degrees of freedom. So mean square is going to be sum of squares divided by the degrees of freedom. As you see, we took SSR divided by 1, we take SSE divided by n minus 2, and these are our mean squares. If we take the mean squares and divide them, we divide by MSE, which is our mean square error, then the mean square regression divided by the mean square error gives us an F value. And we can get the p-value by saying, okay, what's the probability that F is greater than this table value? And here, F will have 1 degree of freedom in the numerator and n minus 2 degrees of freedom in the denominator. And as you see, this 1 goes here with that one, and the n minus 2 goes with that one. So it makes sense what we're saying about the degrees of freedom. So as I mentioned, SSR is equal to, I can solve for SSR, and that would be equal to SSY minus SSE, and sum of squares. So this is from SAS, and although we're not going to use SAS in this course, you might run into SAS at some time during your career. It's widely used in academia and in consulting and large businesses. So here's our ANOVA table. And we see that we have the model error, and they say corrected total. So we would call this SSY, and here is SSE, as you can see, and then SSR is SSY minus SSE, of course. And then here's our mean square, and again, you can see that you could get the calculator and take this and divide it by 28, and you're going to get the 299.765. And you see that this number came across because it's divided by 1. we take this number divided by this number, and we end up with the F value. And in this case, the probability that f would be greater than this under the null hypothesis, and the null hypothesis is that the model is not significant, and that probability is less than 0.0001. So this is highly significant. So that means the model is highly significant because this is such a small p-value. Okay. So let's talk about the fundamental equation of regression. And that is, we've been talking about it, that the total variation in the response variable is equal to the variation due to the regression plus the unexplained residual variation. So in this ANOVA table, sometimes it's called SSR for residual, or SS resid, and sometimes this is called SS regression. So the notation can be quite confusing if you don't know which one is which. So, oh yeah, we called it regression, and it could be SSM for model. Okay. So this is our fundamental equation of regression, and so SSY equals SSR plus SSE, and we can prove this. I don't know if I mentioned it earlier, but in a more rigorous course, we would definitely go through this proof. I have provided it here for you. There's a couple of techniques in order to make this work, and I'll let you look through that on your own, but we're not going to concern ourselves with proving this on a test or anything like that. So this is just for your information only. And so let's look at, so we have SSR, and that is y hat minus y bar. So let's look over in our equation and find y hat minus y bar. So this is, here's y bar, here's y hat, and here's y. And so this amount from y bar to y hat is the explained. And then we look at SSE, and that's y minus y hat. That's our residuals, and that's unexplained, error or variation. And then the total is the sum of those. So there you have it, the relationship. And it's nice that we have these quantities that certainly add up. If you take 1 here and 2 here and add them up, you definitely get 3, but they're not summed, or they're not squared. So here, if we take the squares of those and add them all up, we still have the equality. That's quite interesting, really. So now let's talk about some statistics here. So it is known from statistical theory, in our university, you take our probability theory, and you'd learn this, that if SSR and SSE, they are statistically independent. That's just true. So they are. And if we're testing that beta 1 is equal to 0, and if that's true, this is under the null hypothesis, in that case, SSR over sigma squared has a chi-squared distribution with 1 degree of freedom, and SSE over sigma squared has a chi-squared with n minus 2 degrees of freedom. And again, this is under the assumption of normality as far as the error. And we talked about that as an assumption for regression. And so that still has to hold. And if that's true, then we know again from probability theory that a chi-squared random variable divided by its degrees of freedom over another chi-squared, and there should be a parenthesis here, over another chi-squared random variable that are independent provides us an F statistic. And again, you see the degrees of freedom of 1 here and n minus 2 here, and that's F of 1 with 1 degree of freedom in the numerator, n minus 2 in the denominator. And so I just talked about that next sentence. So we've already constructed a t-test for this in Chapter 5, and that was in this format, beta minus beta 1 hat over the standard deviation of beta 1 hat. And that is a t-distribution with n minus 2 degrees of freedom. And this is equivalent to the F degrees of freedom, F test, because for nu, that's the Greek letter nu, degrees of freedom, we have the f of 1, and this is important. As long as the numerator degree of freedom is 1, then the t squared of nu, whatever the degrees of freedom in the denominator is, if you square the t, you get an f distribution. So that relationship holds. Okay. We're certainly not going to prove that. And we have that from probability theory again, that standard normal random variable divided by the square root of a chi-squared random variable divided by its degrees of freedom gives us a standard normal. Okay, and this is only when when our standard normal and our chi-squared random variables are independent. Okay, they have to be independent. So we have f, 1 degree of freedom in the numerator, nu degrees of freedom in the denominator, and 1 minus alpha. That is equal to the t with nu degrees of freedom, 1 minus alpha over 2 squared. Okay, so the two-sided test for h naught beta 1 equals 0 is equivalent to the f test for h naught beta 1 equals 0. So these are equivalent tests. You're going to get the same answer, whichever one you use. So let's go back to an example and look at this. And so we have this readout, and again we have here our ANOVA table, and you see source. So this is the title up through here. And then you have model, error, corrected total. You can see, and we looked at this a little bit before. And so here's our f value. And this quantity here is s squared y given x. So that's what this value is. So if you're doing any calculations, you might want to know that. Here's the root mean square. That's the square root of this, and that is s sub y given x. And here's r squared right here. And then we have the f statistic. Oh, and notice if you square this t statistic, you'll get the f statistic. Down here, we have parameter estimates, and because it's a straight line, we only have one parameter estimate. For beta 1, where we have this parameter estimate, and we have this standard error with a t value here, you can square this value, you're going to get the 21.33. Okay. And it has, of course, the same, although this is so small, you can't tell that they're the same, but they are the same p-value as well. All right, so that was Chapter 7. Please don't forget to scan your lecture notes by midnight of the date listed on the course calendar. Be neat for you. Update your formula sheet. If you have any questions, come to virtual office hours. If you can't come to office hours and you need some help, you can email me. We might be able to meet. If not, send me a picture of your work. Send me a picture of the problem, because I may not have access to the problem, and I'll help you as soon as I can. Take care, and we'll see you next time.